Okay, let's get started. So this is the first seminar of our Tartan SLAM series, organized by the Air Lab and the Robot Perception Lab at CMU. I'm Wenshan Wang from the Air Lab. I'm so excited to host this event. Excited to see many people join us from Zoom. Yeah, and also we have a lot of people joining us from YouTube stream channel. So we have a 40 minutes presentation today by Professor Sebastian Scherer from the Air Lab, who is also a main organizer of this event. And we then are going to have 20 minutes discussion on SLAM questions. And because we have so many people joining us today, so during the SLAM discussion session, please put your questions in the chat or on the YouTube chat so that we can organize those questions and answer them like one by one. You can also raise your hand in the Zoom meeting. Yeah, the host, our organizers will unmute then you can ask the questions. And I'm very happy to introduce Professor Sebastian Scherer. He is the Associate Research Professor at Robotics Institute at CMU. So in general, his research focuses on advancing state-of-the-art real-world autonomy algorithms, and his research spans from real-time perception to motion planning with strong safety guarantees. So his work on 4-scale autonomous helicopter flight has received several awards, including being nominated for the Collier Trophy in 2018. So he is currently leading the Subterranean Challenge Team Explorer, which won the first place in the Eternal Circuit and won the second place in the Urban Circuit. So regarding SLAM, he has done a lot of work in SLAM, so which he will be telling us about in a minute. So I really enjoy and I'm very grateful to have the opportunity to work with him for in the last 3 years. He always encourages us to do the more practical research, which will really work on the real robot platform. So without any further delay, let's welcome Basti to give us the talk.
Yeah, thanks. Thanks, Wenshan. Thanks for the nice introduction. So I mean, it's really exciting, and we started to think about this series before I get into all the technical details. We tried to organize like a little summer school each summer to focus on some topics, and we realized that SLAM was kind of the thing that people are really excited about. So we figured, okay, let's try and put something together that brings people together. Just to give you some idea, about 800 people are signed up. I don't know how many want to listen to what I have to say, but about 50 companies and institutions, just to give you an idea. And I mean, we can see that there's a lot of demand for this, and hopefully, and we hope that this is not just essentially some kind of paper advertising in some sense, but what we want to get, we want to get as many people up to speed as we can, and we'll kind of have some more info on this, and then also kind of link that to the latest research, but also get some kind of critical thinking going on, are we going in the right directions? What are some of the challenges that are out there? So we have set up this question system that was posted in the chat. So if you have questions, please put them in there. We can kind of upload the questions. And I guess YouTube is also, and the chat here is also an option, but maybe kind of second preferred to that question system. And then we'll try and collate these together. We hope that this is the first in a set of multiple series, and there are many awesome researchers that we couldn't get to in this first series, and we would like to get there. And you would really want to kind of get a breadth of different talks, from some higher level talks to some kind of nitty-gritty, really in-depth talks, and get a broader audience also up to speed. Now, so here are kind of the 5 easy steps on how to get up to speed in SLAM. And we'll post the slides, and there's basically each one of these is a link. First, linear algebra, conditional probability are kind of basics. Then in the Air Lab summer school from last year, there's a series of about 5 talks on SLAM, graph learning, and so on, and each of these has associated code with it that you can walk through, and we'll have some help sessions in Discord. So that's kind of fourth link here. So in Discord, it's kind of like Slack if you're more familiar with Slack, but open. And the idea is that we can build a community there, and you can ask questions. And then once you're ready with this, then you're in some sense dangerous. And then go look at some of the keynotes from last year's CVPR's talk, and then the questions and the discussion, I think, will be a lot more informed, and you'll also have like a good understanding on some of the probably more advanced and really kind of pushing the limit talks that are coming up. Just in case you're not as familiar here, just a couple of quick terms. We often talk about pose. Pose just means position and orientation. Odometry is how you get from one pose to the next pose. Localization is where you are, and mapping is the map. Drift is how much you've drifted over time. And then loop closure means if you come back to the same place, how you've made a loop, and how do you adjust that loop. So I want to talk a little bit about what is SLAM and where does this actually come from. I mean, in some sense, it's a very old idea. Imagine you were exploring the United States, going kind of from the East Coast to the West Coast. You would have been doing SLAM, right? So you'd look at, okay, here's some landmarks that I'm on the map. So you figure out, where am I on the map? You'll see some hilltops, you see some rivers, and you say, okay, these are the landmarks. Then you've identified yourself with respect to that map, and then you would incrementally, add new features to that map. Work your way through the US until you've built a map. I mean, this is a simplification. Then you can do some things to globally constrain the position. But imagine if you didn't have stars, that's what you would be doing, is essentially looking at landmarks. And this is the basic idea behind SLAM. So you build a map. Initially, you figure out where you are, update the map, and keep going. Now, that was the original meaning. Since then, SLAM has turned into more of an umbrella term. And initially, it was really just focused on the estimation problem. Now you think about different types of estimation. You're figuring out where dynamic objects are, some of the semantic segmentation of these maps, and actually thinking a lot more about the maps. A lot of different types of sensors, cameras, radar, GPS, everything fused together. And sometimes SLAM isn't actually even SLAM, it just refers to odometry. So there's a lot of different ways this term is used. But in the broad sense, it's all about mapping and estimation. Now, one vision that I think that we are very interested in, but I think is a little general, and you might hear some of this coming up in some of the other talks, is people want to build this kind of grand system where you have multiple agents aware of each other, where they are with respect to each other, build this map, and have this unified kind of representation between different modules where you can have a semantic sense of what these modules are in a very high resolution map. Now, and we work on parts of this, and you'll see this as well. But I think one of the things that we are very interested in is how can we make robust systems, and that is really the key to push things forward from a robotics perspective. Efficiency and accuracy are often what a lot of research papers focus on, and part of that is also just it's easy to measure, right? Like accuracy is very easy to measure, efficiency is very easy to measure. Robustness depends on many factors and is a little more difficult to measure. And you can think about, we want to use these robots often in what's also referred to as like 3D situation, right? Dull, dirty, dangerous, and these often come with very difficult operating conditions. You can imagine dust, fogs, fire, smoke, and we want to be able to localize ourselves with respect to this. So this is kind of one of the axes we've looked at a lot. Now, just to give you an idea, this is from some of our flight tests for the DARPA Subterranean Challenge. So this drone is exploring here inside a mine. And you can see that, even though it was unintentional, you run into these situations where we create a lot of obscurance. We just kick up dust, for example, and have to deal with it. Now, some other things that we look at is, for example, bridge inspection. And we want to be able to have these really large-scale models, but with very high resolution in situations that are also very difficult for SLAM. Right? It's narrow passages, which are bad for laser scans. It's dark, we have to bring our own lighting, but we want to maintain this really high resolution. And the other challenge that we look at is how do we know where we are using very lightweight sensors where we minimize what we have to add. So could we, for example, replace or augment GPS in case of failures and just know where we are based on an image. Now, before I talk some of our research, I want to just give you a little bit of a high-level overview of where this work stands. So they're currently, SLAM is a big area. What we'll focus on here a lot is visual and LiDAR sensors as the modality, but there are many other alternatives, and of course, GPS is one of the main things. It's things with radar, many other ways you can do sonar, SLAM, but often the methods are quite similar. So there's, in the LiDAR SLAM side, you have 2D SLAM, 3D SLAM, and deep LiDAR SLAM, and we'll bring up some examples later on. On the visual side, there's different combinations of sensor, more than one camera, depth cameras, different types of ways of processing the data. And then you can go beyond a single sensor and try and fuse multiple sensors together. So this could be cameras and IMUs or cameras and LiDARs to get your position. So here are just some of the more famous approaches, and we'll leave these slides here for you to look at as a good reference if you want to kind of catch up on some of the kind of popular approaches. And so LiDAR SLAM can be very good and is a very popular approach. And the performance, one of the downsides is, of course, the cost, and the performance depends on the geometry of the environment. Vision, on the other hand, is more attractive, has sensors, it's lower cost, but it's very the performance depends a lot on the texture. On the high level for visual SLAM, there are 3 types of methods. So sparse visual SLAM looks at features, image features, and tries to track those. And then dense methods essentially try to take the whole image and compute relative motion. And semi-dense methods are essentially somewhere in between. Now, a single sensor is very vulnerable to not look at the right place or to be in the wrong space. So fusing it with another sensor allows you to get better performance. So here, fusing it with an IMU, for example, gives you a lot of advantages. And for monocular methods also allows you to get metric information. One type of method that has become very popular is this idea of using neural networks for state estimation. Now, some of the hope with these methods is that you could potentially overcome limitations in regular methods where you need good texture. So and also potentially get some semantic information. And we'll talk a little bit more about this later. And then if you have more than one sensor available, then you can potentially do even better than this. So you can see here using laser and visual, laser and IMU, or event camera, IMU and visual data, or thermal cameras and IMU. That's some examples. I'd like to talk a little bit next about how to evaluate SLAM systems before we go a lot into this, into the details. Now, there's many popular data sets, especially, for example, the Kitty data set is very popular, or UROC, or the TOM RGPD data is a kind of free popular sets of data that are used for SLAM development. And these data sets are good, but I think sometimes the SLAM community has gotten a little trapped in those data sets. For example, if you're developing a learning-based algorithm, you should not just use the Kitty data set. You can use it for testing, but you should not use it for training. And part of the reason is you can see also in the bottom figure is a distribution of what motions they actually have in them, right? Because the Kitty data set is taken on a car, it only has one axis of translation and one axis of rotation. And so this makes it very ill-constrained for learning if you wanted to actually estimate full 3D motion. And so we looked at this, and we saw many of these learning-based algorithms work extremely well on Kitty, and it was just kind of painful to see. And so part of this then drove the development of the TartanAir data set. The idea was to get a really broad set of data, multimodal labels, so you have stereo, visual, camera, depth, and also get some really more challenging situations that we would face in real life, and get motion that actually covers the full spectrum. Another thing we wanted to look at is how can we get a better measure of robustness. And so two popular metrics are absolute trajectory error and relative pose error they're used to measure SLAM algorithms. However, these metrics are not very good to represent the robustness of an algorithm. So what we looked at as a metric is to say what we call the valid rate, so which is how long does an algorithm think it's valid compared to the total length. Now, this is not the best metric, and we're still working on some better metrics, and I would love to get your input to kind of try and improve what would be a good metric to measure robustness. But regardless, based on this valid rate, you can see that the TartanAir dataset is much more challenging, and it's but it doesn't mean it's impossible. It's just a more difficult dataset. And but you can see, for example, on Kitty, which is a very nice time of day when the data is collected, well motion, nice constrained motion, the algorithm performs great. Right, so you can get a sense of some of the limitations of the other data sets. We're currently working on the TartanAir V2 dataset, and if you're interested in contributing, please let us know. It will have more than 100 environments, more than 2,000 trajectories, more than 2 million frames. In addition to some of the visual sensors, we'll be adding IMU LiDAR, spherical camera, fisheye camera, event camera, and radar, and then also adding new motion patterns and dynamic objects and more weather. so things are going to get much more realistic, and I think will be an even bigger challenge, but hopefully also a source that can help learning-based approaches in particular. If you're interested, here is the link to the data set and code and the website. And so, Wenshan will give a talk later in the series and she'll talk in much more detail about the data set and what we're doing. Maybe even give you a preview of V2. And then, so once you have this kind of data set and evaluation, one of the first things we want to do is state estimation. So based on the TartanAir data set, now we can develop a learning-based algorithm that actually has a chance of being able to be generalizable because the motion is very random and the environments are diverse enough. So we developed a visual odometry method, so just camera, no IMU or other sensors to do visual odometry. And what's kind of unique is just that one is that it generalizes, but the other thing is also generalizes to arbitrary cameras. You can basically pass in calibration parameters and it will just work. And so here's an example of this method has never seen actual real-world training data and is running on actual real data, here in Pittsburgh, running around the house. And we can see it's also quite aggressive motion. Here, orb slam essentially loses tracking because of motion blur. But one of the advantages of the learning-based methods is that they can handle motion blur quite a bit better. And so the method has comparable performance to non-learning based methods, but is more robust in challenging situations. So it's never seen, for example, Kitty or Europe in our situations. And you'll hear much more about this. But I just wanted to kind of give you an idea. Now here's now kind of moving to the next concept. So the idea is, how can we increase this robustness? While I think these learning-based methods have a lot of potential, it will still take some time for them to be robust enough for and to have enough confidence that we'll use them on real systems. And so one of the big things that can increase robustness is to try and use multiple modalities to estimate your position. So for the DARPA Subterranean Challenge, we developed a method that fuses various sensors to build and is able to fuse these sensors in a way that allows them to drop off and still have a robust estimate. And the way we do this is to really focus around the IMU. So the IMU is the core sensor, and an IMU can give you very good estimates if you are able to constrain it with some other sensors. And in this situation, the other sensors are a visual camera and LiDAR. And as long as you can detect when they're ill-constrained and only use the information that they're constrained with well, then you can do much better in terms of state estimation. So here you can see a smooth, narrow corridor where LiDAR SLAM will have a really hard time because it can't see the end and there's not enough constraints along the tunnel. LiO SLAM is another popular LiDAR mapping method. Now here, superodometry uses the camera to constrain, especially along the corridor. But the LiDAR still helps the overall estimate. So it's not just LiDAR switching between the two, it's basically merging the constraints from both methods. And that gives us the ability to be quite robust to a large range of situations that we also expect to encounter, for example, in the DARPA Subterranean Challenge. Now, here's another example where the camera, for example, drops out. So we're going from inside a dark room, so camera gets lost. And the key is really that superodometry is able to recognize here that the camera is not giving good data and then can focus on the LiDAR. And again, we're trying to test here pretty aggressive motion to really ensure that the method is robust. So here's another example of, for example, LiDAR and inertial, where you can see that in these extreme dust situations, there are not enough constraints available from LiDAR to constrain the motion. In this situation, this method essentially coasts off the IMU for a little bit, and then until it's out of the dust cloud. Okay, and in the interest of time, I'll skip some of the other things. We've tested this method on multiple platforms, and you'll hear more about this kind of in August, I think, is the idea. Okay, so one of the other areas that that we're very interested in is, can we figure out where we are in 3D just based on an image and a map that is just a point cloud and does not have any appearance associated with it? And you could imagine there are kind of two motivations for this. One is that often you have only a 3D map and you might not have the appearance with it. The other thing is, if you can do it without appearance, it is more robust to the appearance variation. And then the other part that we want to do is, if we have places we've been to, can we learn how to recognize those? So one way to do this localization is to try and extract edges and then detect edges in 2D and then extract edges in 3D, try to match them to do your estimation. And so one of the things that we did for this is to develop a new line detector that does not depend on the camera parameters, because that will allow us to use it directly without having to undistort images. And also because we like to use kind of wide field of view fisheye cameras that give us much more context. We want to be able to detect these lines in this wide field of view. And so once we have these lines, we can now match to the 3D maps and have this drift-free localization. So here, just kind of a quick example of this, where we're trying to imagine we have, we're just doing regular odometry versus the matching. Having this matching allows us to localize without drifting. And you can see the matches from the from 2D and 3D in the red and green colors. Now, once we so this line matching works very well in man-made structures, but if you want this system to work also in natural environments and outdoors, we need a way to be able to generalize. So one other way we've looked at this is to try and learn a descriptor that can match well between range images and visual images. And so I won't go into the details here, but the idea is to learn this matching module and then learn a similarity module that is robust to appearance changes. So here are two examples of localizing in the point cloud based on the 360 videos, both indoors and outdoors. So just to kind of give you a sense of that this method can generalize across different appearances and still match in the map. And then we can also take this method then to match for aerial localization. And so one of the tricky different things here is that once you get really high, the system degrades to a 2D localization. Once you lower, it's still a 3D localization. Now, often when we talked earlier about loop closure, and so one of the things you have to do is to try and find a match between different, when you come back to the same place. Now, you can use this loop closure to essentially do localization if you had a prior image, or you could use it to adjust your whole map. And this, one of the ideas we've looked at is to use lifelong graph learning to try and both improve the feature extraction and matching as well as the place recognition. And the advantage there is that as the system can improve its feature extraction as you move along, and also scale to this kind of lifelong setting where you imagine you want to have a robot operating for a long time. And so the idea is kind of twofold. One is we have a memory module that updates in real time as we operate, and will adapt to improve the matching. And then the second one is to use memory replay to avoid catastrophic forgetting. And so you can see that with this kind of feature detector, even with very bad images, so on the left is kind of analog video from a blimp, and here on the right is a video from a simulation with some fog in it that makes typical feature detectors fail. We can still get very good feature matches. And also, since we build up this memory, we can get matches from quite far ago. So you can kind of see here this plus 5,800 number means, for example, how many frames in the past this. To learn more about this, here's the info, and we'll put that in the link. Now, kind of last part that I wanted to quickly show you is how can we use these lower cost sensors to try and get some really good maps in high resolution maps in these kind of more difficult situations. So the two kind of strategies we use to increase robustness. One is that our sensors have a really large field of view. So we have, for example, a rotating LiDAR or a large slider. The other thing is that we look at localizability estimation to tell us when the problems degraded. And then we fuse all the measurements. We have two cameras and a LiDAR together with the IMU together to get a really good sparse model, and then we densify this model to get very good high resolution maps. And so our goal is, often when you do structure for motion, right, where you just upload a set of images, you have to, you can get very high resolution data, but you can't get the scale. So really what our approach allows you is to get the resolution at the larger scale. And so you can see here that if you, the scale from blue to red is the error from 0 to half a meter. You can see if you do this kind of joint LiDAR camera optimization, you can get very accurate maps compared to a ground truth model, which we took with a survey scanner. And so here's one example on how we get some really big maps. So this is a 65-meter long tunnel. It has 2 billion points. So the idea is really to give you essentially a virtualized reality, right? So you have, you can go from a large scale and really zoom into a millimeter or sub-millimeter level. And so to make all this happen, we use a cluster and everything's parallelized and so on. There's like a whole part of just making that part work. But the idea here is really that this can give you some good advantages, especially for infrastructure inspection. Now, the other part of the pipeline that I can glance over is how we get good stereo. And one of the big challenges we have is that we have 4K images, so with a byte baseline. So we're looking at disparities of several hundred pixels to really get millimeter or sub-millimeter accuracy. And to process this with traditional stereo algorithms is not feasible, and even with learning-based methods at this resolution, you need too much RAM, so it's impossible to process. So the way we handle this is to first process a downsampled image with a learning-based algorithm called OR stereo, and then in the second step, upsample that image and process it step by step. And this allows us to get much higher resolution stereo and using less GPU memory. And so here you can see some examples of using the first phase of our algorithm and upsampling it in the second phase in a comparison with traditional learning-based methods. And then here on the left, it's kind of the same example. And you can see some of the fine features that we are able to pick up with the 4K images that essentially drop out once you have to downsample. And so once you put all this together, we can then use this to build a high resolution model. And here we're just showing an example of a beam. You can also see kind of the drone in action here. So we're taking a lot of images, and actually just image quality in itself is a good challenge when you're really trying to get this kind of high resolution. So with this high resolution reconstruction, the LiDAR map gives you some more context. And then we can analyze this map in various ways. So we build a surface mesh, we automatically fill the holes, then mask for crack detection, then detect some cracks in that model, and then can look at these cracks. Also, we can look at these cracks with respect to an abstracted model. So this model would be then used to annotate the cracks better, and then we can also analyze this mesh to see how well how much effect the defect would have, how much load it can take, and so on. So you can find more information about this at these links. Okay, just to kind of summarize, and I know I went a little fast, but I wanted to leave enough time for questions. So we'll have this Tartan Slam series. For now, it's 10 talks. We think about adding essentially a second series because there's a lot of interest here. Please sign up on Discord and let your friends know if you think this is interesting for them. And the SLAM problem is still a challenging problem in many situations where robustness and efficiency are often more important than accuracy. And in our lab, we're really trying to push more towards the robustness to try and see if we can make these methods work very well from a robotics perspective. And talked about state estimation, the localization, lifelong feature learning, and high resolution mapping. Okay. Thanks everybody. And then also I wanted to mention, there's a large team of people behind this, and I didn't have time to mention exactly who was working on everything, but there's a lot of, the core work is done by the team mentioned here. Also like to thank the people is the key to organizing this, Shivo, Nikhil, Venture, and Henry, and Brady. And I think now we come to the fun part, which is open questions. Now I have one for myself that I wanted to kind of bring out first and kind of maybe get you thinking a little bit. SLAM is a core part of robotics, but there's a tendency to also blame everything on SLAM, right? Like if SLAM doesn't work, then it's like, fix the SLAM system. But there's often a robustness performance trade-off that can be made, right? Often you don't need the full state estimate to do what you need to do. And one other way to think about it is if you're more a control person, if you just had a PID loop, it might be more robust, but maybe lower performance than if you had a really good model. And that model isn't correct. So just as a quick example, here's a drone flying inside a tunnel with a laser that doesn't have enough constraints to run 2D SLAM. Like you wouldn't be able to run a 2D SLAM algorithm here, but it's still able to fly just fine by learning a direct mapping from sensor to controller action. Right. So I think just something to think about. Are we relying on SLAM too much? And then so here are just some questions that we put out first, but let's see.
Okay. Yeah,
how do we want to do this?
I think I saw action raised hand. Yeah, would you like to respond to Basti's top question?
Hi, I wanted to ask how is the ground truth determined in these data sets, pose and the map?
So for sim, it's easy, but for real, we use various techniques. The two key tools are total station and a survey scanner.
Yeah, I think in the Kitty data sets, they just generate the data based on the LiDAR localization and GPS localization. And in Europe, they have like indoor environment, so they set up a motion capture system to generate the ground truth for SLAM system. Yeah.
Thank you.
Okay, thanks.
So I see there's also some questions in the question document. Which one? Maybe you can read the question and then, or somebody can read the question.
Yeah, I'll pick up the most upvoted questions from the list. So the first is, what's the best SLAM system out there to run on an edge device, like low compute?
So I think that is a loaded question. So there's not one system to rule them all. This would be my opinion. It depends on what your sensor is and what you're trying to do. So I think, I don't think there's a single one, and I encourage you to look at the tutorials to kind of get a better understanding of the trade-offs, right? I think the idea is to not necessarily turn you into a SLAM researcher, but to know enough when to choose what algorithm and what configuration of sensors.
Right. Yeah. Also, I saw Shibo add a comment like that. This depends very much on the environments.
Yes.
Yeah. You need to balance a lot of things. The next question is, what role do you think do you see of visual place recognition in SLAM, and what are some key future directions at the intersection of these two fields?
Right. So I think place recognition is very important, and it's going to become even more important once you have augmented reality, right? Like you want to be able to anchor what you see and what you do to a global coordinate frame. And so if you can have robust localization, it really can help you. And so, imagine somebody inspecting a bridge that has some virtual reality goggles can now, annotate something on the bridge, and it gets associated with a global coordinate system. And so, part of what we are trying to push with the 2D to 3D localization is exactly along those lines, where often you have 3D, but you need some connection to 2D, and you might not have had images for 2D data before.
Yeah. Also, Max also added comments like, visual place recognition like already plays an important role in the loop closure in current SLAM system. Will be a lot of more applications like last mile delivery mobile robots, like blind people navigation under challenging indoor-outdoor conditions. Yeah. Okay. Next question. A lot of people would love to hear more on research internship positions at CMU. Or
Sure, we can have a separate talk on this. I mean, I think there's there's a lot of work to be done right now. I mean, at least the Air Lab is pretty full, I think. But there's a lot going on, outside in terms of overall CMU, and kind of the standard process for summer internships. A really good program is the Robotics Institute Summer Scholars, and it's really kind of like an intense summer internship program. There's some community around it. I think that's what I would recommend for undergraduate students who are really kind of interested in getting into this area.
And what are the good ways to quantify the performance of a SLAM algorithm? I think we briefly talked about this in the presentation.
Yes, right. So we talked about essentially AT and
RPE.
Right, and then so it depends on if you're actually evaluating a SLAM system or an odometry, what you're looking for, right? So for some of the bridge inspection, for example, we looked at differences in map, if you're really interested in the map. But your robustness, I think, is still something that would be good to get some discussion started, because I think there isn't a good established metric that we have been able to kind of hammer down that that isn't there. So.
Okay. Yeah. Question. Do you have a question?
Hi. Great talk, Basti. And I just wanted to ask a question. This is more of a general, I guess, to get your thoughts on usually like my opinion as a SLAM researcher, and feel free to just chip in, or, you know, if you have a slightly different belief, I'd be curious to know yours. Is SLAM is largely, it's a means to an end. It's not an end in itself. Like, you're building a map to do something in the end. So one aspect that I've been thinking about deeply is how do you tightly integrate, like, you know, SLAM with respect to a task? Like, you'd ideally want these systems to be coupled. And
right,
like, do you have any thoughts about, I guess that's one avenue for learning. I see a question on your slide about, does learning have a place in SLAM? So I'd be curious to hear more thoughts about integration with tasks.
Right. And I think, you know, maybe this kind of last video was part of the idea that, you know, we didn't in this video, there's still enough data in the LiDAR to do the task, which is essentially navigate down the tunnel, even though there isn't enough data to do 2D SLAM, right? And so I think that was kind of part of the idea, and I agree. You know, it's in some sense, you know, kind of one of the reasons why we don't have a mocap is it's like becomes a crutch, right? you're tied to the mocap, and you get addicted to the mocap, and so I think it is definitely something to think about. Is I agree, it's a means to an end, especially on the robotics side. Now there is, you know, there are many cases where essentially having this common defined frame of reference is very valuable. You know, for essentially comes down to mapping, right? Like if you're trying to map a bridge, you really want to know, you know, where it is on the bridge that something is, right? Because that's just how it is. And but there are, from a robotics task perspective, there are many other ways you can go about in terms of topological mapping, or, you know, some of these other ideas, combining it directly with the action, where you can get away with less state, right? Sometimes you might just care about roll and pitch or something like this.
Yeah, makes sense.
And so in terms of learning, I think the question then becomes, you know, is it, where do you introduce that? Like, do you learn a direct mapping? Do you perform a traditional algorithm up to the degrees of freedom you're interested in? I think there's a lot of open questions there.
Okay. Yeah. The next question from the audience on YouTube is, are there any visual SLAM system that works both day and night?
Yeah, all of them, if you have good enough lights. so, I mean, basically, but I think it comes down to, you know, do you still get enough image features? And then the question is, does the noise in the images affect you enough. And so I guess one of the things we found is that in bad lighting situations, typically dense methods are more robust because you don't have to rely on an accurate localization of a feature, which can move around with your noise or might not get detected.
Yeah, I think that depends heavily on like how much light you can get.
Yes.
It's too dark, then no visual stem can deal with that.
Yeah, or you have to use other modalities like thermal or lighter.
Yeah, or IMU, to compensate.
Yes. Yeah.
Another question: what are the sensor modalities are better suited for snow and foggy conditions? Would thermal plus IMU plus radar work?
Yeah, I mean, foggy, I think thermal, yes, I think that thermal plus IMU plus radar is a good combination. Snow is a little tricky. We haven't done a lot of things in snow. But I think on a road, for example, I think it would work fine. But overland and everything's pristine, maybe there's not enough thermal contrast.
Related question, how are some ways to address the brownout effects that occurred when flying in an enclosured, dusty environment?
Right. So, I mean, brownout is something that we encounter a lot. And on Monday, actually, in the ICRA workshop, we'll talk a little bit more about this kind of dusty environments. But in terms of visual and lidar sensors, there's some amount of filtering you can do in the lidar data to get rid of some of the dust. But if you're actually in a real helicopter brownout situation, the two strategies are either to not use lidar and visual data, but instead use certain band of thermal and radar is more effective. Or the other way is to just basically remember before you kick up the dust.
Michael, go ahead.
Yeah, very good talk. Thanks, Sebastian. How do you decide between using deep learning and traditional methods? So, for example, backends.
Yes, yeah. So I think this, and I think that is, I think the jury on practical methods is still out, and I hopefully with TartanAir V2 and some of the new algorithms for tests will have some sense if they can be an option, right? I mean, right now I think they've only been shown in very limited situations, but I think there is a potential for deep learning to overcome some of the difficult situations where our engineering assumptions when we build an algorithm fail, basically. Like, so we would assume, let's say, good texture to extract a feature. If that texture isn't there, then you can't extract a feature, but a learning algorithm might be able to pick up enough context to still give you information. Or, for example, a blurry image actually contains a lot of information, right? It actually is some sense of optical flow. And so that could give you, can actually give you some information, but it's difficult to use. So I think on the backend side, you're the expert, so I don't have a lot of opinions on the backend. So probably you'd be better to answer that.
Okay, thanks.
Yeah, Roshan also asked a similar question. Is the learning-based methods in the learning-based methods are classical methods like bundle adjustment, scan match, and post-graph optimization still used in the backend? And in other words, is the learning restricted to feature extraction and data association? I think this is related to.
This might be a good question for you, Michael. Okay. Did you get the question? Are you muted? We still can't hear you.
Okay, now can you hear me?
Yes.
Good. I also missed some of the question. Can you repeat?
Oh yeah. So in learning basics, the question is in the learning-based methods, are classical methods like bundle adjustment, scan matching, post-graph optimization still used in the backend? So it's learning-based method restricted to feature extraction and data association.
I think there have been some attempts to use learning on the backend also, but I'm not convinced yet that that is the right way to go. Right, so we basically understand how the geometry works and we can encode that. I'm not completely sure in the long term what the answer is, because there are some limitations to the backend which relate to robustness. And so the question is, can you overcome these with deep learning methods? That might be a possibility. But if we just talk about traditional backends, I don't really see beyond speeding something up or so. I don't see how to do better than, better than using the geometry, right? If you learn that, it's not going to generalize as well, is what I think. But I think the jury is out on that, and this might change in the future.
May I ask, what are the shortcomings in current backend system, like a few examples?
So I guess I will talk next week a bit more about that also. I think the main issue is that there's mostly that Gaussian noise assumption, and that underlies all of the efficient solvers. And so that really deals poorly with if something goes wrong, it doesn't handle that well. And there are a couple of methods to get around it, but none of them are really perfect or really addressing the problem fully. And that's really an open research problem still.
Okay, yeah, we are looking forward to the talk next week. Yeah. Yeah, we are over time now. Should we keep the question? I'll keep coming. Should we extend this a little bit more?
I mean, we can maybe take five more minutes, and then I think the other thing is we have the Discord set up. It was posted in the chat here, and maybe also on YouTube. And so feel free to keep on discussing there. We'll kind of check in. And I think it might be a good way to kind of build a little bit of a community around this.
Yes. Next question from Samali from the Zoom. Would you like to?
Hey, Dr. Sebastian and the team. Thanks for the talk and the series. I have a question about sensor fusion. So let's say that we have two sensors, a camera, which gets a VO output at 3 Hertz, and an encoder, which gives an odometry estimates at 30 Hertz. So what is the best way to fuse? And is UKF loose coupling would be a valid option here, because there's a huge difference between the two frequencies? And also, what does tight coupling means in this case? Could you just give me?
Right. So I think I mean, even a EKF I think would probably work in this situation. Anytime you have to go to a UKF, be sure to know why you need the uncentered part. Like, is it really non-Gaussian? And then the other thing is, I think that should work fine to fuse the measurements. In terms of loosely versus tightly coupled, I mean, loosely, kind of in the simple sense, means you have two different odometries and you're just kind of fusing them together, right? So there's already some filtering happening on the vision side to get you this. If you wanted to do tightly coupled, you would take let's say the landmark feature measurements or something like this, and then combine them with the odometry in one big problem to try and optimize the poles.
Okay, cool. Next question: Are you guys working on active SLAM? What's its potentials? Would love to hear your take on it.
So I guess what's not directly, I think. I mean, the part of it is in terms of exploration and object detection and so on. Sometimes the way, for example, for bridge inspection, trying to map certain areas, you could think about as active SLAM. But I think Michael might be doing some work on active SLAM a bit more than we are, for example.
Yeah, I think the question also related to the question Basti put out, like whether we need accurate SLAM algorithms. Like if we have active SLAM, so yeah, we first need to be aware where the SLAM is not accurate.
Right.
Then we can do some like explicit exploration, like look into some place with more features to find out.
Right. And we have looked at this for bridge inspection, and I think I forgot now actually showed some examples on the localizability estimation, where we are basically saying, oh, if you go to this location, you will be lost, or here you will know where you are. And so the idea is, you can avoid where you get lost. So, and that I think is a good idea.
Yeah. Some people are asking like how can contribute to the TartanAir dataset. Yeah, you can just send me an email. Yeah, I can talk to you later.
Yes, mention an email, and there's, as you can see, we're pretty ambitious here, but I think it has a chance to become a really useful utility. If you're interested, love to have you contribute.
I think I almost covered the questions in the list here.
Okay.
Yeah.
Awesome. Yeah, so thanks everybody for dialing in to the talk, and I think we'll see you next week at 12:30, right?
Yeah.
Yeah. Okay.
See you then.
Great. Thanks. See you.